A financial model under risk has a single known probability distribution over prices. The distribution is calibrated. Expected returns are computable. Financial uncertainty is different. The distribution structure itself is unknown. The decision maker faces a family of admissible models, not a single calibrated distribution. Under model risk, expected returns are computed against a single probability measure. A unique scalar guides portfolio construction. Under model uncertainty, each admissible model produces a different expected return. Expected returns form a set. No canonical scalar value exists. There is no unique portfolio optimization target. Mean-variance optimization selects the portfolio that maximizes expected return for a given risk level. This requires a unique expected return vector. Under model uncertainty, the efficient frontier becomes a set, not a curve. The optimization problem is ill-defined. The argmax cannot be applied to a set of efficient frontiers. Multiple financial models can fit the same historical return data equally well. Model selection procedures do not resolve which distribution governs future returns. Expected return estimates remain model-dependent. Data cannot distinguish between admissible models. Ambiguity about the probability model persists after calibration. Without a unique expected return, the optimization criterion shifts from expectations to bounds. The worst-case rule selects the portfolio that maximizes the minimum return across all admissible models. This treats model uncertainty as adversarial. The worst admissible model governs portfolio evaluation. Robustness replaces expected value maximization. Standard financial optimization assumes a known probability measure. Under model uncertainty, that assumption fails. The efficient frontier is not a curve, it is a region. Expected utility cannot be maximized without a unique model. Model uncertainty requires robust portfolio strategies. This is a structural limit of standard financial optimization.